Hello, everyone. So in this presentation, we will talk about the network communication on Aurora, and we will focus on two communication libraries. The first one is, of course, MPI, which is used by parallel HPC simulations, or what we refer to now as traditional HPC. The second library is 1CCL, which is used to scale machine learning training across nodes on Intel hardware. This work includes many contributions from many colleagues across Intel, Argonne National Lab, and HPE, but I want to specifically mention Vitali and Maria, who contributed significantly to this talk. Okay, so you have probably seen some variant of this slide, which show the high-level overview of the Aurora architecture. These are the updated rankings for Aurora from this week. It remains one of only 3 exascale systems on the top 500 list currently. It's also the second system on the HPL MXP benchmark, which uses mixed precision to better represent wider range of applications, including machine learning workloads. And I think it's now the fourth on the HPCG benchmark. Now, these benchmarks alone, if we take each one of them, they don't represent wide range of HPC applications. But if we combine them together, we can see that the top system that we have nowadays, Aurora and also Frontier and El Capitan, are well balanced because, as you saw this week, they perform well on all of these benchmarks, which cover double precision, low precision, and also memory performance from the HPC benchmark. Aurora is a very huge system. It contains more than 60,000 GPUs and more than 20,000 CPUs. All of these are connected through an HPE Slingshot network. Aurora currently is the largest deployment of the Slingshot network. It consists of 166 compute groups, 8 storage groups, and 1 service group. All of these are connected through a Dragonfly network. So in order to travel from one group to another, ideally we need at most 3 switch-to-switch hubs, one within the source group, and then we need one switch, a global link between the different groups, and then another one in the destination group. Of course, if we have a network contention, then the adaptive routing topology will select a different route, usually a longer one, to avoid the contention. Each of these groups is a Cray cabinet, and it had 64 nodes and 32 switches. And all of these have all-to-all connection between them. This is a block diagram of the Aurora node. The Aurora node consists of 2 sockets. So each, you can see it's symmetrical. The upper half is 1 socket and the second one is 1 socket. Each CPU socket have 64 gigabytes of HBM memory, and it also connects to 512 gigabytes of DDR memory. Each socket also connects to 3 PVC GPUs. Each one has 2 sockets, which you can see in the orange here. And for this, we're using PCIe Gen 5 connections. Now also, each socket connects to 4 NICs or network interface cards, and the NICs use PCIe Gen 4. So in order to connect the Gen 5 CPU to the Gen 4 NICs, we need to use a PCIe switch, which you see here. The 2 sockets are also connected through a UPI link. It uses 3 UPI links, which have limited bandwidth. So in order to improve the performance, you want to avoid the cross-socket communication. Now, moving to the MPI implementation on Aurora. Aurora uses an open source MPITS implementation, which is tuned for Aurora and also for larger scale systems. It doesn't have Intel MPI or Cray MPI implementation. It only uses the MPITS implementation. This implementation is GPU aware by default, which means we can directly use pointer to GPU memories within the MPI calls. This simplifies the development of GPU's code because we can directly move the data, and we can avoid moving the data unnecessarily from the GPU to the host, then to the NIC. But this does have a performance penalty. In terms of the performance itself, the execution, the initialization time can take longer when we have the GPU aware, and it also can consume a larger amount of memory. So if the application doesn't use MPI aware GPU aware, we can disable it using this environment variable. The penalty in the initialization time is not significant, but if the application itself is very short, it might become significant, and then we can disable it with this environment variable. Now, as I mentioned earlier, each socket in Aurora has 4 NICs, and then we have 8 NICs total. But in Aurora, the MPI assignment to NICs happen on a socket basis. So all the MPI processes within a socket will be assigned to the NICs within that socket in a round-robin fashion. So if the MPI processes are not distributed evenly between the 2 sockets, some of the NICs will remain underutilized, and that, of course, will lead to performance degradation. Currently, the MPIT's implementation in Aurora allows for 1 NIC per MPI process, and multiple MPI processes can use a single NIC. The choice on how we choose the number of MPI processes depend mainly on the application, because if we choose small number of MPI processes, some of the NICs will become underutilized, and the off-node bandwidth will be impacted. But if we use many MPI processes, we might end up with a contention on the NIC, and that will also lead to performance degradation. Now, how to choose the optimal size, that depends on the application characteristic. We need to take into account the communication pattern, how the application uses the GPUs and the memory system, and then that will determine the optimal number of MPI processes. Locality is very important for the performance. As I mentioned, the 2 sockets are connected with UPI links, which will significantly impact the performance. So we want to avoid the cross-socket communication. So we want to have all the MPI processes, all the GPUs, all the NICs, and all the memory and NUMA systems within the same socket. Now, for the NIC assignment, this is done by default in the MPITs within the same socket. For the NUMA and for the GPUs, Aurora does have good defaults that prioritize locality, but defaults usually change, so it's better to have explicit assignment for the NUMA and for the GPUs. And on Aurora, this can be done through environment variables, so we can use this to specify the affinity of the GPU or the GPU tile. And we can use NUMA-aware tools, the regular NUMA-CTL or libNUMA, in order to pin to a certain memory system. Okay, so in the next few slides, I will go over some MPI benchmark results on Aurora when we're using both the CPU memory or the GPU memory. The first figure here shows the point-to-point latency when we increase the number of MPI processes for different message sizes. And in this case, the MPI buffers are located on the host memory. And for the first figure here, we are using a single NIC. So all the MPI processes, they are bound to a single socket and a single NIC, which can be done using this environment variable. You can see here for small message sizes, the latency is fixed as we increase the number of MPI ranks at around 2 microseconds. And this shows that we can increase the number of MPI processes, and they can share the same NIC with the small penalty in terms of the latency. When we increase the message size further, we see a jump in the latency from 64 to 128 bytes. And this is likely because now the message buffering starts using the host memory instead of the NIC SRAM memory. Another important performance metric is the off-node bandwidth. So we're communicating between 2 CPUs in this case from 2 different nodes. But we are pinning the MPI processes to only 1 socket. So when we are increasing the number of MPI processes, but they are using the same 4 NICs within the socket. And in this case, we start with 1 MPI process, so we are using only 1 NIC, and we increase it up to this dark red line, which represent the 4 MPI processes. So in this case, we are using the 4 NICs in the system. And we see a linear performance improvement in this case, which is expected because as we are increasing, we are able to use all the 4 NICs within the socket. And each socket usually gives us 23 gigabytes per second. So when we increase, we have the linear improvement up to around 90 gigabytes per second. But this is not enough to saturate the NIC, and adding an extra MPI rank results in better performance in this case. Next, we look at the performance when we are using MPI buffers located within the GPU memory. And in the first figure here, we are also using a single NIC within a socket, and each MPI process uses a different GPU. So in that case, for example, if it's a 3 GPUs, we're using 3 MPI ranks, one per GPU, and all three ranks are sharing the same NIC. And in this case, you can see that one GPU is not able to saturate the NIC, and we're not reaching the expected 23 gigabytes per second. And as we increase the number of ranks and the number of GPUs, we are able to achieve the expected performance. Next, we look at the off-node bandwidth. And similar to the previous slide, we are having the same, increasing the number of MPI processes, and they are sharing the 4 NICs within the socket. So in this case, for MPI processes, we will have 1 MPI process per NIC, but because we have only 3 GPUs, 2 of the ranks will use the same GPU. And in this case, we are able to reach an aggregate bandwidth of around 70 gigabytes per second. When we were using the host memory, it was around 90 gigabytes. So there is a difference between using a host memory or the GPU memory. And in this case, this performance reduction is due to limitation on the communication path between the GPU and the NIC. The last performance metric we want to look at is the MPI collective. The MPIC supports all the traditional collective communication, but here we are looking at the MPI or reduce. And here we look at the performance for different message sizes as we increase the nodes count up to 2,000 nodes. Within MPIC, I think similar to many other MPI implementation, it automatically select different algorithms for each of the collectives based on the number of nodes, number of MPI processes per node, and the number of message sizes. And we can see the impact on this figure here. We see a reduction in the latency based on different message sizes, and this suggests that the underneath algorithm is changing as we increase the number of nodes. Now you see that in this figure, the message sizes are relatively small, which is expected for MPI for HPC applications with MPIC. But if you're running a machine learning workload, for example, on Aurora, you will want to use one CCL, which provides a different set of collectives and different set of algorithms. And Anthony will share more on this.
So for machine learning application, there is a communication library called 1CCL that provide a number of primitives. And the primitives are, the typical all reduce, reduction, all gather, reduce, scatter, all to all, and even point to point. So it's built on top of the fast link between the GPU, that's called XE-link for Aurora system, for intra-node communication among the GPUs, and then across node using Slingshot. And it has a number of algorithms that it can adapt to. A ring algorithm is something that's simple to set up, good for a small number of nodes, because the ring depends on the number of nodes participating in the rings, and if there are a large number of nodes, then you sort of pay for that, depending on the number of nodes. But for something like a power of 2, then Rabin-Sacno would be a better algorithm, so it's adaptive. And it uses either MPI or OFI as a data transport layer. And so it's likely integrated with the machine learning framework like PyTorch, TensorFlow, and other data distributed training mechanism, and which large language model training and inferencing can use. So this was a measure on Aurora. up to 8,000 nodes. And it's a little challenging to actually collect data on large number of nodes because you need a reservation that large, and a large reservation is a little hard to come by. So the one that performed best is the bottom one, which is Raven-Sapner, and this one is optimized for power of 2. So if it's not power of 2, then now the one CCM has to decide what algorithm to choose. If you're close to power of 2, then it can perform some sort of reduction to get to power of 2, and then you Raven-Sapner, or if it's not, then I'll have to pick a different algorithm. So another one is the direct. Direct here use MPI transport layer, and it performed close to Raven-Sapner. And then here is the mystery. So it diverges after 512 node or so. The latency become higher. We think there's some issue with this measurement. So but we have to remeasure when we get the allocation again. But it should stay close to Raven-Sapner because we're still within the power of 2. The green one is the ring, and as expected, after 256 node, you can see that as you double the number of nodes, the average time also increases with the number of nodes. And the other option are double tree and recursive, and they seem to perform similarly. Longer latency than Raven-Sapner or direct. But after some point, after 2K nodes, they perform better than the ring algorithm. The double tree right now is not pipeline, so once the optimization applied, then it will perform better than what we see now. So I go a bit into the application that use the MPI mechanism, communication mechanism as well, one CCL. So these are the benchmark that many of you know already. So HPL is one of them. So shown here is the overall time of performance per flop at you over time. And performance does go down because initially you have a very high compute amount, and so it's less limited by communication, and after some time compute become much less, and that's when communication can impact performance. So for HPL, as you probably aware of, it was Aurora able to achieve just a bit over 1 exaflop, and that put it on the number 3 now on the top 500. And scaling efficiency over time is 78, almost 79%. For HPL MXP, the scaling was better at 9,500 nodes at 89%. HACK is an application, I would say it's a workload, and it's traditional HPC workloads that very efficient in scaling. It has some like 3 pattern of communication. One is when it used a distributed 3D FFT. The second one is near neighbor communication, and the third one is all reduced collective. And the all reduced tend to be small, like as you see across the parallel application that I will show. There are barriers, right, that just communicate or perform all reduction on a single 8 byte, and so it's latency sensitive. And for hack, to improve parallelism, it uses 96 rank panels, and as Huda mentioned, right, when you have so many ranks, they share the same NICs, and as you share the same NIC, they can be bandwidth limited. And so for this application, it is a single NIC is shared by 12 MPA processors, and that could reduce the bandwidth portion. But it scaled quite well. So at 8,000 nodes here, we see that it's 97% efficiency in scaling. Now for LAMs, efficiency is lower at 80%. And for LAMs, they are the near neighbor communication, but it's frequent and also the loop time is very short. So you can see last bullet item there, the loop time is around 3 seconds, and then you have an all reduced for that barrier. So at smaller node count, it is less sensitive because at smaller node count, the variation in the system is less. When you go to a high number of nodes, there could be timeout in the fabric. There could be retry. There could be some hiccup in the network that can impact that 3-second performance. So to really improve this application, you have to make sure that the compute portion is sufficiently large compared to the frequency of communication. So for LAMs, if you increase the number of atoms per node, then scaling would be much better. So neckbone is another workload, and based on NIC 5000 application, it has a lot of compute and this one application where it can offload to the GPU and for most of the execution time. So it's very efficient, and communication is infrequent. So here scaling is like up to 95% at 4K nodes. And again, as you can see here, the last bullet is the all reduced rate. You can see that very small, like 8 byte, and again, this kind of reduction is latency sensitive. And for machine learning application, it uses a 1CCO library for collector communication. And the large application that would run on the Aurora supercomputer is the mprot DPO that Argonne presented at, I think, submitted to the Golden Bell Prize in 2024. It was one of the finalists. And that one runs on several systems, and you can see that on Aurora, the blue bar at the top there is the number of node that it can node and number of token that it can scale to, and it is a linear. So here, this application has a lot of data transfer, right? All these are reduced that occur, and the data size is sufficiently large to make it scalable. For tuning this kind of application, we actually use a smaller machine learning application called Retina 50. And for that application, we reduce the batch size to like the bare minimum of 16 images per second. So that make the compute time very small and expose the communication layer. And then we use that to optimize 1CCL. Let's see, I think that it. Do we have any more slide? Yeah. Any question?
Any questions from the audience yet?
Very interesting talk.
Thank you.
Have you considered the I/O performance of the system? Maybe probably it's out of the scope, but
so I/O is interesting. So Aurora supercomputer has several file system to have the home directory, which is served by one form of cluster. So it doesn't have a huge number of servers. Then there is something called Gecko, which is an read-only compressed file system, and that is used for software like a library like OneCCL or the compiler or other library software. And then you have a larger cluster system called Flare, where you actually put your data set there. And then yet on top of that, you have DAOs, which is really high bandwidth. It can provide around 25 terabyte per second bandwidth. And that is where you want to put, a large data set there. So we use a whole range of these file systems for a whole class of application, from traditional HPC to LLM, where you have a large data set, to in some cases we actually run a single process, independent process, but multiple times. And that really put stress on I/O because each process perform their own I/O. And so we have one case where we use a machine learning application, and we want to explore the hyperparameter search. So you run pretty much the same application multiple times. In this case, we ran 48 ranks per node. And if you multiply that by 10,000 nodes, you have 480,000 ranks. And if each of them go to the file system to read the file to the data set, then that would pretty much overcome any file system. So for this type of application, it's good to perform one read from the file system and then use the slingshot network to broadcast to other nodes, and that's what we did. So Argonne wrote a Python-based utility where you do that single read and then it broadcasts to all the nodes using Slingshot, so that pretty much any file system can handle that. However, that's for reading data, but for writing, if each process tries to write some data, then that can also too much data for a file system. So, for example, for machine learning, they tend to be very verbose and it output a lot to the log file, or it can do checkpointing. In that case, if those sizes are smaller than a terabyte or so, it's good to use class temp on the node. That is RAM disk, which is memory based. So you store all the intermediate data and logging information during the run on the local disk of the compute nodes. And then either periodically or at the end of your run, then you can selectively send the data back to the file system. Otherwise, it's just too much for the file system.
Thank you.
Let's thank our speakers one more time.